Hey folks, here are the solutions to the Unit 5 homework questions, and these are from the Day 2 and Day 3 homework. So this is quotient rule and then the combination questions handout that combines the quotient rule and the product rule together. So the first one we had asked here was 232, number 5A. We want to find the equation of the tangent to the curve at this point. And it is kind of nice that they give us the whole point, like the x and y values of that point, because then we don't have to sub in x equals 0 into the original function to figure out what that y value would be. So we're just looking for the derivative, y prime, going from here. Remember that it's the denominator. So 1 plus e to the x times the derivative of the numerator, which is 2e to the x. Let's kind of keep that up there. Minus the numerator, which is 2e to the x, times the derivative of the denominator, which is just e to the x, all over the denominator squared. So 1 plus e to the x squared. And I would definitely want to simplify this a little bit. And at the very least on the top here, factoring out 2e to the x, because that's a common factor in both. You will find, especially with exponential, where the derivative stays the same, you're going to typically have some good common factoring that will happen. So 1 plus e to the x from the first one, and then minus e to the x. And that cleans this up really nicely. So 1 plus e to the x squared on the bottom. So we see those two canceling out, and we're just left with a 1, which gives us just 2 e to the x on top over 1 plus e to the x all squared. So then I would say at x equals 0, what's this derivative equal to? Because we don't have that function notation here for the y equals, but we can list out what our x value is. So 2 times e to the 0 over 1 plus e to the 0 squared. So on top, we get 2, because e to the 0 is 1. And then on the bottom, 1 plus 1 squared, or 2 squared, so 2 over 4, which is 1/2. So that's our m value. That's our slope of the tangent is 1/2. And our point is 0, 1. And kind of, again, conveniently enough, that, if you recognize, is our b value, because that is the y-intercept. So you could go through and sub in x and y and m and solve for b, but you'll just get 1. So that's y equals 1/2 x plus 1 is the equation of that tangent. So this one, using quotient rule, I think what likely is the biggest issue here is rewriting this without that square root. So that square root is around the entire 3 to the x on top. So I'm going to rewrite this as a 1/2. And then using our exponent rules, 3 to the exponent x over 2 over x squared. And now I'll take the derivative from there. Remember that the notation, if you just kind of have equal signs, that implies that it's the exact same as the one above. So this is all still f at x. When I'm taking my derivative, that's when I would put f prime at x equals. And I probably should have just done this up at the top. I want to have enough room. So f prime at x is the denominator, so my x squared, times the derivative of the numerator. And this is going to have a few pieces, because the derivative of 3 to the exponent anything is 3 to that same exponent times ln 3 times the derivative of the exponent. So maybe I'll put brackets here, just keep it nice and clean. So the derivative of x over 2, we could write, just a note, if you have x over 2, sometimes people see that a lot better to do the derivative of if they pull out the 1/2 in front as a coefficient. So the derivative of that is 1/2. So that's the first times the derivative of the second. And I'm going to scoot this out of the way. Whoop. There we go. Now I'll do minus, so bottom times the derivative of the top minus the top, which is 3 to the x over 2, times the derivative of the bottom, which is just 2x, because that was an x squared, all over the denominator squared. So x squared squared again. So again, looking for some common factors, I definitely see that both of these terms have a 3 to the x over 2. And then I also see some common factors because I've got an x squared and an x. So those are the common factors I would pull out. So I'll pull out an x, and then 3 to the exponent x over 2. And then I'll be left with here x ln 3 over 2 minus 2, because I factored out that x, all over x to the 4th. Now a couple of things still to clean up. I'm going to reduce that x with the x to the 4th on the bottom, so I'll have 3 left. And I really don't like the fraction in a fraction there, like that 2 on the bottom is not good news. So I'm going to multiply top and bottom by 2 over 2, and I'll just distribute this 2 into the brackets just to clear that fraction there. So here I get 3 to the exponent x over 2, and then I have x ln 3, because that 2 will reduce on the bottom, minus 4 over 2x cubed on the bottom. So I've cleared out my fractions and fractions. It's factored as much as I can, and I've reduced the x's top and bottom. So that, I would say, is the simplified form. Okay, now we are into some trig derivatives. So nothing really to simplify here before I take the derivative. Y prime is the bottom, so 1 plus cos x times the derivative of the top, which is cos x, minus the top, so minus sine x, times the derivative of the bottom. So the derivative of that denominator is negative sine x, because the derivative of 1 is 0. The derivative of cos x is negative sine x. All over the denominator squared. Then I'm definitely going to say that this is cos x, kind of distribute that in there, plus cos squared x, and then with this kind of double negative situation there, this would be plus sine squared x over 1 plus cos x squared. We know that we see the identity here, cos x plus sine x, that's 1. So then cos x plus 1 over 1 plus cos x squared, that will reduce. So I'll have a 1 on the top and just that 1 plus cos x on the bottom. So cleaning things up as much as you can, if you see some easy identities to use, that's always a good idea, because we're going to want to be able to solve for the zeros and the restrictions on all of our derivative functions as we go into looking at optimization problems. So this one's kind of interesting. If you forget the expression that results when differentiating the tangent function, how can you do that with an identity? So if we had, excuse me, f at x equals tan x, what's the identity that we know for that? That's sine x over cos x. So now that we know the quotient rule, we can figure out what the derivative of tan x is using this identity. So f prime at x, that's the bottom. So cos x times the derivative of the top, which is also cos x, minus the numerator, the top, so sine x times the derivative of the bottom, which is negative sine x, all over the denominator squared. So here we get cos squared x plus, with that double negative, sine squared x over cos squared x. And of course, that's our Pythagorean identity on top. And so it's 1 over cos squared x, which is just secant squared x. And that's really where the derivative of tangent comes from, just taking the derivative of sine over cos. Okay. Now this is looking at the worksheet. So here we have a product of two functions. So the kind of bigger piece is that this is the product rule of those two functions. But when we do the derivative of this one, we're going to have a quotient rule when we do that derivative. So kind of looking at, if we kind of look at our things here, we'd have, so the first times the derivative of the second plus the second times the derivative of the first. But when we do this derivative of the second, that's going to have quotient rule. So that's what we're going to have to work through. So I think I will rewrite this just because there's that root x that I think people won't really like, and make that an x to the 1/2. So then when we have the derivative, we've got our first factor, so this stays the same, x cubed plus 2x plus e to the x. And then we have the derivative of the second. So we're going to take the derivative of that quotient rule one. So this one is the bottom times the derivative of the top minus the top times the derivative of the bottom, which is 1/2 x to the negative 1/2, all over, I don't know why I did a square bracket there, x to the 1/2 squared. So that gets a little bit messy. Of course, I'm just going to kind of erase this thinking, planning part. Now we have the second piece. So this same thing, x minus 1 over x to the 1/2 times the derivative of the second, or of the first, pardon me. So 3x squared plus 2 plus e to the x. So now it's this one that's really quite messy and likely going to kind of cause us some problems to simplify, but I think we can do it. So I'm going to leave this x cubed plus 2x plus e to the x, and then just work in here. So this is x to the 1/2, and I'm going to be multiplying in here. So minus 1/2 x to the 1/2, because here when I'm multiplying this x here by this x to the 1/2, I'm adding the exponent. So 1 plus negative 1/2 is 1/2. And then the next one, I'm going to have plus 1/2 x to the negative 1/2 all over on the bottom and x. So here I do have some like terms, and I think I'm going to need a whole nother board here. Okay. So when we simplify in here at least a little bit, I get 1/2 x to the 1/2 plus 1/2 x to the negative 1/2. And that's going to be an important thing to be able to factor. So I am going to just kind of add a slide in here, keeping everything the same, and I'll just get myself some more space by copying and putting what I'm doing here on the top of a new slide. Just going to pause this for a sec while I work that out. Okay, so I have this set up on with a bit of a blank slate here. This is just the same thing from before. This is what I really want to focus on. Like, this could clean up a little bit, but especially here with it like 2 terms times 3 terms, and this e to the x sort of throws it off to a point where I don't think that it's worth simplifying that really too much at all. Here, there definitely are things that we should simplify. Keep working in that piece, that factor. So 2x plus e to the x, not going to touch that for now. On the top here, this is an important thing to be able to do, and it's this factoring here, thinking about how can I factor out some kind of factor of x. So on the top, I'm going to factor out a 1/2, and when we're common factoring, we always take out the smallest exponent of x. So that's x to the negative 1/2, because that's smaller than 1/2. So then what would you multiply here? X to what exponent times x to the negative 1/2. Remember that you're adding those exponents. So you're thinking negative 1/2 plus something equals positive 1/2, and that's just a 1. And then plus that whole thing would have factored out, right? We've got a 1/2 x to the negative 1/2. That whole thing, it was my common factor. So that's just 1 over x on the bottom. And then here, I'm just going to keep this kind of as is, right? This is x minus 1, 3x squared plus 2 plus e to the x over x to the 1/2. Now I'm going to, last step, just kind of clean this up. I've got a 1/2 on top. I'll just put the 2 on the bottom, and also anything with negative exponents, it's a single term, just throw that down onto the bottom and simplify. So here, x cubed plus 2x plus e to the x times x plus 1 just kind of making sure that that shouldn't be a minus. Okay, times x plus 1 there. And then this whole thing on the bottom, like I said, that 1/2 has a 2 going down. And when I put this x to the negative 1/2 down here, it'll be positive 1/2 plus that 1. So I'm going to make that x to the 3 over 2 plus x minus 1, 3x squared plus 2 plus e to the x over x to the 1/2. Now, we might kind of think about, should we get a common denominator here? And what's really stopping me is that if we got a common denominator, it would only make sense if we were going to FOIL everything in and collect like terms. And we would for sure have some like terms, like I see we get an x cubed there, and we've got an x cubed, but we also have this e to the x. So if it was just polynomial, then I might FOIL that all in and see if I would get like even a quartic on the top that might be able to factor, but this e to the x is going to make it too messy, so I would just leave it there. Another one from the worksheet. Now this one you can look at in a number of different ways, but if you do this without foiling it all in, what we're going to basically look at is that these are the product of two functions, and one of those functions is also a product rule. So this is a little bit arbitrary. I'm just going to kind of put brackets around there and there. And you could group those in any kind of way that you wanted. Like somebody else might have grouped these two together and this one separate. That would be fine. So f prime at x is, that's going to be the first factor. So x minus 7 times x squared plus 4x. And this is actually just a little bit of a mental exercise. I would probably just FOIL out that first pair, especially before doing the derivative, because I think it would probably be easier. But this is good kind of practice of working your head around multiple derivative rules applied at a time. So that's the first factor, like the blue brackets, times the derivative of the second. So that's negative x to the negative 2 minus 1. And then plus the second, so x to the negative 1 minus x times the derivative of the first. And when we're doing the derivative of the first, that's a product rule itself. We're going to do product rule to take the derivative of the stuff in those blue brackets. So here I get the first, x minus 7 times the derivative of the second, which is 2x plus 4, plus the second, which is x squared plus 4x, times the derivative of the first, which is just 1. Now cleaning things up really as much as I can, which I don't know how much that's going to be. Definitely in this big square brackets, I'm going to FOIL stuff out and see if I can kind of collect like terms and clean that up a little bit. So this would be 2x squared plus 4x, was that a 7? Minus 14x minus 28 plus x squared plus 4x. So again, keeping this all pretty consistent. And here we've got 3x squared just trying to see. And then plus 8, so minus 6x minus 28. And then, yeah, that looks like kind of probably where I would stop, just kind of debating here. The one thing that I maybe don't like is those negative exponents in here, like there and there. So that I might actually factor out. So from this one, I'm going to factor out negative x to the negative 2. So that, again, is like my lowest exponent of x. So when I keep, these ones are just going to stay the same. Oh, actually, I see a common factor in there. Should have noticed that one too. So this guy is that negative x to the negative 2 is getting factored out of there, and I'll also factor out a common factor of x from there. just kind of color coding there. So here I've got x minus 7 and then x plus 4. And now careful here, if I factor out negative x to the negative 2, then that's a 1. And what would we multiply x to the negative 2 by to get just x to the 0? So how many do we have to add? And that would be an x squared. So 1 plus x squared. And I'll kind of do this similar thing here, x to the negative 1. So this would be 1 minus, and that would also be x squared. 3x squared minus 6x minus 28. I think I got that all right. Now these guys, this here is x to the negative 1, or negative x to the negative 1. So I can common factor that that whole thing is x to the negative 1. And then I've got an x to the negative 1 there. That's a common factor. So here I'm going to pull out x to the negative 1, or maybe negative x to the negative 1. And then I would have x minus 7, x plus 4, 1 plus x squared, minus, and then here I would look and see if I could factor these. I guess I can make that 1 plus x 1 minus x with a difference of squares. And if you wanted, you could write that on the denominator, make it over x, but you don't really have to. I'm kind of on the verge of thinking that we could FOIL these all out, but I feel like my line is kind of quadratic, and this is already like a quadratic times a quadratic, so that's going to be quartic. That's probably too big for me to do just in case I can factor it, and I would get a quartic there as well. So I'm kind of not going to FOIL that out. If it was quadratic, for sure. If it's a cubic and you think things are going to cancel or you're going to have to solve it anyway, then I would still do it. But kind of this, like an x squared and an x squared, that's going to get just a bit too big and too messy and probably not be able to factor anyway. So I would not do that one. Okay, this one's kind of interesting. The tangent line of f at the point x equals 4 is given by the equation y equals 5x minus 7. So this tells us a few things. This tells us that the derivative, so f prime at x, is 5, because that is the slope of the tangent line. And then we can also say at x equals 4, the equation of this line just touches the point. So y is 13. So that tells us, sorry, I should have had a 4 here. So we know that f prime at 4 is 5 and f at 4 is 13. This is a good thinking question. It's not too tricky of calculations, but you have to really recognize what information you have. So the equation of this tangent line gives us 2 pieces of information. The y value when x equals 4 of function f is 13, and the derivative is 5. Okay, excuse me. So if we were going to take the derivative of g at x, I'm just going to rewrite like we usually do this as x to the 1/2 times f at x. So the derivative here, g prime at x, is the first x to the 1/2 times the derivative of the second. We don't know what that is, but it's f prime at x, plus the second f at x times the derivative of the first. So it's 1/2 x to the negative 1/2. So here we could simplify for sure, but we're just asked to find the slope of the tangent, so we want to know what's g prime at 4. So since I'm just subbing in here, I wouldn't simplify, but I definitely would normally to factor out that x to the negative 1/2. So here we get 4 to the exponent 1/2 times f prime at 4 plus f at 4 times 1/2 times 4 to the negative 1/2. So that is 2, 4 to the exponent 1/2 is 2 times f prime at 4 we know is 5 plus f at 4, which is 13, times 1/2 4 to the exponent negative 1/2 is 1 over 2. That's 1 over the square root of 4. So we get 10 plus 13 over 4. That would be 40 over 4 plus 13, so 53 over 4. So the derivative at x equals 4 of our g at x function is 53 over 4. And that's everything from today's homework questions.